Hello, and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about the source-free RC circuit. And essentially what we want to do in this video is go from this circuit here, call this 1, which is a regular RC circuit with a source or a VS connected to it. And we want to analyze what happens to this voltage VC, or the voltage across the capacitor, when we disconnect this voltage source, right? So what happens when we come to the second circuit here, and what happens to VC when we come to the second circuit. So that's the point of the video. And before we dive into some mathematical equations, we first want to define the source-free RC circuit. A quick definition is a source-free RC circuit occurs when its DC source, so the RC circuit has a DC source, so when its DC source is suddenly disconnected, the energy already stored in the capacitor is released / dissipated to the resistor / load of that circuit. All right. So I'm going to give two examples of this, some real life examples, so you can see what this looks like. So imagine you have a wall and you have your charger plugged into the wall, and you have your charger cord connected to, let's just say, a speaker. All right. What you're going to notice is there's normally an LED that indicates the user that the speaker is charging, or that the speaker is on, right? And what happens is, in this charger, there's normally capacitors here, miniature or large capacitors that store charge. And what you're going to notice is, once you disconnect this charger from the wall, so let's say you disconnect this, and this LED starts to turn off, it's not going to turn off right away. It's going to slowly dim out, right? So from bright red to maybe a lighter red color, and then all of it then goes away. Again, this happens extremely fast. The reason why this happens is a result of this capacitor here discharging its current to the speaker after you disconnect it from the wall. And when you disconnect it from the wall, it becomes a source-free RC circuit, right? So that is the time period where we're considering the source-free RC circuit in a real-life application. All right. So another example is, consider you have two walls. All right. And in this wall, you have a charger and a cord hanging out. And again, remember, this charger normally has some capacitance inside. Again, this is maybe the end of the cord. All right. And you have your cell phone. All right. And what you actually want to do is, you want to bring this charger to this wall. All right. So there's an outlet at this wall here that you want to bring the charger to. And in moving this charger, you plug it into your phone. So essentially the charger gets plugged into your phone, and it's just hanging, right? For a brief second, or less than a second, when you plug it into your phone, you're going to notice your phone vibrate for a tiny bit of a second, right? It's going to vibrate a little bit and stop. At that moment of vibration, right? So essentially what's going on here is, we've connected the charger to a source, right? Your outlet wall, like a 12-volt source. And it's charged up the capacitance. And so when you're trying to move this over here, what actually happens is that charged up capacitance in the charger charges your phone, right? It gets released into a load, which is your phone, right? Dissipated, right? To a resistor or load. And for a brief second, it charges up your phone. All right. And again, once all the current flows out of the capacitor, the phone stops charging. But again, that's an example of this source-free RC circuit. Now, the importance of understanding the source-free RC circuit is because it's a building block to signal processing, right? and filtration, right? So in your hardware, signal processing and filtration, right? Filtering. So in your hardware, if you wanted to create things like a low pass filter, or if you wanted to do decoupling capacitors, right? You need to understand the idea of a source-free RC circuit before we can build on to more circuit like with capacitors in it. So I hope this base allows you to kind of understand or motivates you to kind of understand the reason why we need to study the source-free RC circuit. And now I'm going to dive into some mathematical formulations of this circuit. So what I'm going to do is I'm going to break this down into two cases. So the first case is when t is equals to 0 minus. And what the 0 minus means is essentially a time before 0, right? If you can imagine a time before we disconnect our charger from the wall, right? So what's going to actually happen is current is going to flow from this power supply Vs, and it's going to charge up this capacitor, right? So positive charges on that end and negative charges on this end. Okay. And what we're actually going to have is a circuit that looks like this. After a certain amount of time, once the capacitor charges, we're going to have a circuit that looks like this. And since after the capacitor is done charging, current could no longer flow through it, so it's basically an open circuit. What we end up getting is that so since we have charges here, right, and here, we would get something like I is equals to 0 because R is equals to infinity, right? So current cannot flow through an infinite resistance or through a vacuum or air, open space. Again, this is Vs, this is Rs, and this is R. Okay, so essentially, we can consider that the voltage here, VO or VC of O minus, is equals to what? It's going to be equals to Vs, right? So if I took a voltmeter and I plugged it in here, the positive end here and the negative end here, it would be the same as if I took that same another voltmeter and plugged in its positive terminal here and its negative terminal there. So what could we say then? We could say then that VC of O minus is equals to Vs, which is also equals to V at the instance of 0, right? So the reason for this is because voltage cannot change instantaneously across a capacitor, right? So this voltage here has to equal VO, right? Or the voltage right before 0 minus, and at 0 has to equate. And this is what we call the initial condition. And if you have any concerns about this theory, please check out my capacitor video. I've posted the link in the top right-hand side corner of the video. So the second case is a situation where we then move this switch, right, from position 1 to position 2. So essentially now it's facing here as located in this circuit. So let's go ahead now and analyze this circuit here on the left-hand side. So then what we can do here is we can write a KVL, right? And again, please make sure to check out my video on KVL posted in the top right-hand side corner of this video to fully understand what we're doing here. So what we're going to do is we're going to write a Kirchhoff voltage law equation. So we're going to put a loop here. And we're going to say that the voltage across the resistor R is R times IC. And then the voltage across the capacitor is simply VC is equals to 0. And as a side question, which I will answer at the end of the video, is if we solve for IC, notice that it's going to be a negative value, right? So really quickly, IC is equals to minus VC over R. Why is this negative? Again, please leave your answers down in the comment section below and check at the end of this video to see if you got it correctly. Okay, so let's go back to our equation here. So we notice that IC, so is R, so this is R times C dV over dt plus VC is equals to 0. If you're wondering where we got this equation, I also made a capacitor video. I will post the link in the description below and in the top right hand side corner of this video as well. So please feel free to check out that capacitor video to understand why IC is equals to C dV over dt. So let's keep on going. What I'm going to do now is I'm going to multiply both sides by 1 over RC. And then this is going to be dV. Oops, let me use the same color. This is going to be dV over dt plus 1 over RC. VC is equals to 0. Let me then call this A. Okay. So then this becomes dV over dt plus AVC is equals to 0, where A is equals to 1 over RC. And again, remember, this is for t greater or equals to 0. Okay, so an important notation or an important thing I want to say here is that since this has no source, right? So Vs is gone. We call this a source-free first order differential equation. Okay. And again, this is very, very important. And the equation or the solution to this source-free first order differential equation is what you consider to be the natural response. Okay. And this natural response is a very common term that a lot of people will use. But the natural response is basically the discharging of a capacitor, right? So how will the capacitor's voltage respond when you disconnect the source voltage from it? Okay. So I hope that makes sense. So what I'm going to do now is I'm going to write out the solution. Let me zoom out a little bit to this differential equation. And that will be the conclusion of the video. So the solution. So we have dV C of t over dt plus AVC of t over dt is equals to 0. What I'm going to do is I'm going to move this to the right hand side. So I get dVC of t over dt plus equals to minus AVC of t. So let me go ahead and multiply both sides by dt. So what we're going to get here is, I made a mistake here. This should not be a dt underneath there. So when you multiply both sides by dt, you're going to get dVC of t is equals to minus AVC of t times dt. All right. What I'm going to do now is I'm going to multiply both sides by 1 over VC of t. And what we're going to get here is 1 over VC of t dVC of t is equated to minus AVC A dt. Let me go ahead and take the integral on both sides. When I integrate this, what I get is ln magnitude VC of t is equated to minus a t plus c. I hope everyone sees this. Essentially, this integral is it's with respect to dvc of t, and this integral is in respect to dt, or the change in time. So this is my solution to that integral. And then what I'm going to do is I'm going to take e on both sides. All right. And I'm going to be left with this ln cancels out. This is vc of t is equals to e minus at times e to the c. But if you notice, this is simply just a constant. So ec is just equals to c. And this value here can be positive or negative. And that's important because it allows us to get rid of this magnitude sign. All right. So to conclude, we can say then that therefore VC of t is essentially equals to C1 e to the minus AT. Okay. So we need to then solve for this for this C1. So in order to solve for C1, we remember our case one, where our initial, or case number one, where VC of 0 is the initial condition, and this is essentially equals to VS, so we can use this interchangeably. So what we're going to say is that VC of 0, all right, I'm plugging in 0 into this equation here and here, that is equated to C1 e to the minus a times 0. Essentially, as we know, e to the 0 is simply 1. So then this just becomes C1. So C1 is equals to VC of 0. So again, C1 can be VS or VC of 0. But in order to make it more explicit, I'm going to just consider C1 to be my initial condition. So whatever you get as your initial condition is your C1. So now what I'm going to do is I'm going to write a general equation. Okay. And this general equation is going to be VC of t is equated to VC of 0 times e to the minus AT. But again, we said that A is equals to 1 over RC. So what we can do here is say this is over RC. But 1 over RC, or RC, is what we call this time constant tau. Okay, so that's another very important term. So we say where tau is equals to 1 over A is equals to RC. And tau is what we consider to be the time constant. Okay. And this is a very, very important value, the time constant of a circuit. I don't want to dive too much into what it is, but it's basically for an RC circuit is equals to RC. So then this becomes your general equation right here. So this is the solution, or what we really wanted to get from this source-free RC circuit. If you have any questions on this, please leave them down in the comment section below, and I'll be sure to get back to you. Before we conclude the video, to answer the question why we get a negative in our circuit when we solve for it, for current, it's simply because when we charge the capacitor, current actually flows, right? So positive to negative will actually flow in this direction. So let me consider this big I. But when we wanted to solve for VC of t, we took current to flow in the clockwise direction, right? So it's the opposite of how so let me call this I. So little I is actually equals to minus big I. If you took whichever one you took, you would still get the same equation here. But it's just something to realize in terms of current flow. Okay, if you like the video, please give it a thumbs up. If you have any questions, leave them down in the comment section below. And please subscribe to my YouTube channel. It really helps the algorithm. Thank you.